Welcome back. Now that you have enough knowledge about how steganography works, let's get started with the practical part. I'll show you a tool called Steghide, which is a steganography program that is able to hide data in various types of image and audio files like JPEG, BMP, WAV, or AU file formats. Steghide uses a graph theoretic approach to steganography and can be installed on Linux, Windows, or macOS. On Kali Linux or any other Debian-based distribution, you can simply install Steghide by executing apt install Steghide. Okay, it was installed. We notice that it has a lot of options. In this example, img.jpg will be the cover file and julius_caesar.txt the embedded file. I want to embed or to hide this txt file in the JPEG image. At first, the secret data is compressed and encrypted. Then, a sequence of positions of pixels in the cover file is created based on a pseudo-random number generator initialized with the passphrase. The secret data will be embedded in the pixels at those positions. If those positions do not need to be changed because they already contain the correct value by chance, are sorted out. For audio files, the algorithm is the same, except that audio samples are used instead of pixels. By default, encryption algorithm is Advanced Encryption Standard, which is an extremely strong encryption algorithm. If you want to dive deeper into how Steghide works, read its man page. This is its man page. You'll find here a lot of information. For the following example, I have as a cover file the same picture you've already seen in the previous lecture. I took it by myself using my phone. Inside this picture, I'll embed the tragedy of Julius Caesar by William Shakespeare. I've downloaded it from the Gutenberg project as a text file. This is the Shakespeare's play. I recommend you to have both files in the same directory, the directory where you'll execute Steghide. I have them in the home directory of Kali user in another directory called Stego. In the steganography process, the cover file will be changed, so I'll make a copy of it. I want to have the original as well. So cp, the file, and the copy will be named img_original. Now both images are the same, and we can always check this by calculating their hashes. Like this. It's the same hash, so the files have the same contents. Let's see what's the capacity of the carrier file, the cover file. Steghide info img.jpg. And we see its capacity, almost 140 kilobytes. Let's embed the secret file into the cover file. Steghide embed -cf from cover file and the cover file -ef from embedded file and the embedded file, and that's all. I'm hitting enter. Now it's asking for a passphrase. Always use a strong password of at least 12 random characters, or if you use a passphrase, use at least 6 or 7 random words. Okay, it's done. The secret file was embedded. Now let's open both images. This is the modified image, the one that contains the secret. And this one is the original file. I'm switching between them. They look the same to the naked eye. How could someone detect that there is a secret message hidden in such a file? The easiest way is to compare the Steghide file, the file that contains the message, to the original file using a hash algorithm. There are changed bits in the Steghide file, so its hash will be different. Let's see their hashes. And it's different. We notice that the hashes of these two files are different, so that means the files are different. But if it's so simple to detect the existence of a hidden message, what's the purpose of steganography after all? In this example, I have created a copy of the original image on purpose to make my point and show you this. But in a real-world steganography use case, you should always use unique images. There should be no original image that someone can compare the Steghide file to. Any image that is taken using a digital camera is theoretically unique. You cannot take the same image again. There will be a small difference in light, colors, and so on. Or a print screen could be also unique. Being unique means that there is no other image to compare to, and we've solved the problem. The second way someone can detect that a file contains a secret image is by using Steganalysis. Steganalysis is the study of detecting hidden messages using steganography. This is analogous to cryptanalysis applied to cryptography. The problem is generally handled with statistical analysis. In practice, however, it's extremely complicated to break steganography. Let's move on and try to extract the secret file. In the current working directory, there is also the original file I have embedded. I'm gonna rename it so it won't be overwritten in the extraction process. Perfect. And I'm extracting the embedded file. Steghide extract -sf from Steghide file and the name of the Steghide file, img.jpg. It's asking for the same passphrase and the file was extracted. Let's see if it's the same file. Okay, it seems it's the tragical play of William Shakespeare. I want to be 100% sure that the file was extracted entirely, so I'm checking the hash of both files. And it's the same hash, and that means it's the same file. Okay, that's all about Steghide and steganography. Thank you.